Good afternoon, and welcome to the White House Brain Conference. I'm Meredith Drossback, and I work in the Science Division here at the White House Office of Science and Technology Policy. When the President launched the BRAIN Initiative a year and a half ago, it was with full knowledge that it would take an all-hands-on-deck effort to meet the bold challenge he laid before us. That's why it's great to see so many scholars, innovators, clinicians, and philanthropists here in the room today and online answering that call. Before we dive into our program this afternoon, I have a couple of housekeeping notes. We encourage you to follow along our conversation on Twitter using the hashtag WHBrain. During our Q&A with each panel, we will be taking questions from the audience. So please look for staffers roaming with note cards and pens to submit your questions for the panelists. It is with great pleasure that I welcome you here to the White House. I look forward to our discussion, and I hope that each of us leaves here today with a new idea on how we can play a role in making this collaborative endeavor a success. With that, I'd like to introduce our first speaker. Daria Nestorovich is a graduate student at the University of Utah, where her primary research interest is neural engineering applied to neural prosthetics, specifically deep brain stimulation for Parkinson's disease. She graduated from Duke University this past spring as a Pratt Engineering Fellow and a National Academy of Engineering Grand Challenge Scholar with a major in biomedical engineering and minor in neuroscience. We're so happy to have Daria here today as part of the White House Brain Conference and to tell us a little bit about her experiences before introducing our next speaker. Please join me in welcoming Daria.
All right. As a current graduate student in neural engineering, I am honored to represent the National Academy of Engineering Grand Challenge Scholars Program and graduate students nationwide working to advance our understanding of the brain. Thanks to the BRAIN Initiative and the resulting excitement around neural research, the field of neural engineering is currently experiencing unprecedented funding, which encouraged me to pursue a PhD in the field. The stark reality of science is that funding is often scarcer than many of us would like it to be. This in turn slows down research progress and prevents the goals of large-scale projects from coming to fruition. However, the BRAIN Initiative has already led to the investment of substantial funding aimed at the ambitious and necessary goals of mapping the brain, linking neural activity to behavior, and integrating computation within neuroscience experiments. With a background in biomedical engineering and neuroscience, I earned my bachelor's at Duke University before starting my PhD with Dr. Alan Dorval in the Neural Interfaces track in the Bioengineering program at the University of Utah. As a part of the National Academy of Engineering Grand Challenge Scholars Program, which a colleague of mine will describe later this afternoon, I joined Dr. Warren Grill's neuroprosthesis laboratory at Duke during my freshman year. Our research focused on deep brain stimulation, a neuroprosthetic treatment for the motor symptoms of Parkinson's disease. Despite the disease having been defined for nearly 200 years, we still have a very poor understanding as to its causes, how to slow its progression, and how to prevent it. The BRAIN Initiative is the needed push to not only bring such neurodegenerative diseases to the forefront of society's attention, but to also build large collaborations between research groups, national laboratories, foundations, and companies to actively work towards a solution. DBS has rapidly become the primary surgical intervention for Parkinson's disease, but due to the thousands of parameter combinations and the potential for adverse side effects, it is very difficult to program DBS quickly and efficiently. These difficulties highlight one small example as to why the National Academy of Engineering chose reverse engineer the brain as one of society's greatest engineering challenges of the century. Like many participants here, I want to dedicate my career to help solve this challenge. In graduate school, I'm continuing my work on DBS with the goal of improving treatment efficacy. A problem with DBS that we still see today is that even with the most advanced surgical methods, it is not uncommon for surgeons to miss the center of their target by several millimeters, a distance significant given such a small target for electrode insertion. To combat this, the Dorval group has developed a current steering electrode that allows the applied current from misplaced electrodes to be reshaped to the target area. My part of the project involves creating programming algorithms that incorporate data from MRI images to allow clinicians to automatically program the 10,000 contacts to optimize stimulation for each patient individually. When fully complete, we anticipate that our design will greatly reduce side effects for DBS, while simultaneously improving motor function to a higher degree and in a larger percentage of the patient population. As part of the BRAIN initiative, understanding the brain's connectivity on a larger scale will only lead to a better understanding of Parkinson's disease, which in turn enables our research practices and approaches to be improved. The investments made through the BRAIN initiative will lead to marked improvements in our understanding of the brain, our prevention of neurological disorders, and our treatment of those who have such diseases. Our collective work has the ability to improve the quality of life of countless Americans and their loved ones. With that in mind, I am now privileged to introduce our opening speaker, Dr. John Holdren, Assistant to the President for Science and Technology and Director of the White House Office of Science and Technology Policy. It is due to his leadership in advancing the science and engineering enterprise in the United States that all of us are here today. Dr. Holdren and the Office of Science and Technology Policy have led the charge to meet the challenge of the BRAIN initiative and to fulfill the President's vision of a better understanding of the human brain. I feel honored to be a part of this exciting initiative with each and every one of you here today. Thank you.
Well, thank you, Daria, and let me add a warm welcome on behalf of President Obama to all of you to this first ever White House BRAIN conference. Before going further, I want to offer some thanks to some key folks who are represented in this room, and I want to start with two of my favorite members of Congress, very strong supporters of science and technology in the Congress, Congresswoman Eddie Bernice Johnson, who is the ranking member of the House Committee on Science, Space, and Technology. Congresswoman Johnson. And Congressman Chaka Fattah, who is the ranking member of the Commerce, Justice, and Science Appropriations Subcommittee, which happens to control my budget, as well as a good many other important ones. And Congressman Fattah has been a tireless supporter of initiatives and innovation in neurotechnology and neuroscience in particular. Congressman Fattah. Next, I want to thank my administration colleagues at NIH, at DARPA, at NSF, FDA, and IARPA, who have spent so much time building and shaping this effort into a program that I think is really going to make a positive difference. Your continued partnership is going to be essential going forward, and I particularly want to recognize from the NIH Dr. Story Landis, Director of the National Institute of Neurological Disorders and Stroke. Where is Dr. Landis? And the director of the National Science Foundation, Dr. Franz Cordova, who is down in the front row. I want to acknowledge as well the Department of Energy, which is starting to explore the role that its national labs can play in accelerating progress in brain research. And of course, I want to recognize the many organizations, private sector, philanthropic, civil society organizations, a lot of them represented here today, that have stepped up, that have answered the President's call to action to support the goals of the BRAIN initiative. And last, to everybody in attendance here and to those watching on the webcast, thanks for joining us at this first ever White House BRAIN conference. You know by now that the BRAIN initiative has emerged as one of the administration's top research priorities. In fact, President Obama identified it as one of his administration's grand challenges. Those are 21st century versions of moonshots, audacious but achievable goals to solve tough problems and spark game-changing innovations. The BRAIN initiative is all about accelerating the kinds of research, discovery, and innovative technology applications that can help build a dynamic understanding of how the brain works. One of its aims, obviously, is to build the tools and technologies that researchers will need to uncover the mysteries of brain disorders, which today, as we all know, afflict American families and people around the world. Disorders such as Alzheimer's, Parkinson's disease, depression, and traumatic brain injury. These and other neurological and psychiatric diseases of the brain exact a staggering toll on our society. Today, 100 million Americans suffer from brain disorders at some point in their lives, and that number is expected to grow as our nation's population grows. In addition to getting a better handle on the mechanisms of disorder and potential courses of treatment, the BRAIN Initiative is aiming to revolutionize our understanding of phenomena such as learning, memory, perception, action, and self-awareness, all of which arise from the nearly 100 billion neurons and 100 trillion connections that exist inside our brains. Thus far, scientific enterprise, scientific innovation has brought us a long way toward better understanding certain disease mechanisms and learning and behavioral patterns. In the last decade alone, scientists have made a number of landmark discoveries that today are creating new opportunities to unlock the mysteries of the mind. These include the sequencing of the human genome, the development of new tools for mapping neuronal connections, increasing resolution of imaging technologies, the maturation of nanoscience, and the rise of biological engineering. These breakthroughs have paved the way for unprecedented collaboration and discovery across scientific fields. For instance, by combining advanced genetic and optical techniques, scientists can now use pulses of light to determine how specific cell activities in the brain affect behavior. Similarly, through the integration of neuroscience and physics, researchers can now use high-resolution imaging technologies to observe how the brain is structurally and functionally connected in living humans. Nevertheless, and again, I think everybody in the room knows this, we have a long way to go to achieve the full, clear picture of how the human brain functions at the speed of thought. The kinds of breakthroughs we're looking for in terms of how we treat neurological and psychiatric disease and how we foster better learning outcomes will require a new generation of tools and technologies that enable researchers to record signals from vastly greater numbers of brain cells at vastly greater speeds. A key barrier to such progress has been the lack of available and effective tools to study the brain in action. Today, for instance, researchers cannot adequately measure the real-time interactions of neural circuits. The technologies required to do so with accuracy simply don't exist. This is the particular grand challenge that the BRAIN Initiative seeks to address. It's a big challenge, but the administration and President Obama believe it's an achievable goal. No water up here. I'm going to steal Dr. Paul Alivasatos' water. My apologies, Paul. I bet we can get you a refill. By working together, we can both combat the suffering that is caused by brain disorders and position the United States as a leader in discovering, building, and bringing to market the tools and technologies needed to do so. President Obama has said that America can accomplish anything we set our mind to. This is a great example of a place to prove that. Indeed, the people in this room and the new commitments being announced today are a testament to our determination, and I'm really thrilled to be able to acknowledge those investments now, and more will be said about them later by Tom Khalil. But altogether, the research community, federal agencies, foundations, patient advocacy groups, private research institutes, companies, scientific societies, and individual scientists are aligning more than $300 million in commitments to support the President's BRAIN Initiative. That's in addition to the more than $100 million in commitments made last April when the President first launched the initiative. I'm also encouraged that top neuroscientists have developed a 12-year research strategy to help chart a course for the NIH's contribution to the BRAIN Initiative. These investments and this strategic vision will propel us forward in this very ambitious endeavor. Just imagine if no family had to grapple with the helplessness and heartache of a loved one with Parkinson's or traumatic brain injury. Imagine if Alzheimer's or ALS or chronic depression were eradicated in our lifetimes. And imagine if you, the people in this room, contributed to those breakthroughs. I think you will. One of our nation's next great frontiers is the 3-pound mass between our ears. With your help, we are poised to continue the great American tradition of expanding the horizons of human knowledge through research, science, and innovation. So again, let me just extend my congratulations to all who are taking part in this amazing work, and for the game-changing discoveries and innovations that are sure to emerge from our collective efforts. Let's get to it. Thank you very much.
Thank you, Dr. Holdren. Our first panel of speakers will be talking with us about the cutting-edge technology and tools needed to meet the BRAIN Initiative goals and to address human health challenges. To kick off this discussion, we have Dr. Paul Alivisatos. Paul is an award-winning chemist and internationally recognized authority on the fabrication of nanocrystals and their use in renewable energy applications. He is the director of the Lawrence Berkeley National Laboratory and holds a joint appointment as a professor of chemistry at UC Berkeley, where he continues to teach and mentor an active student research program. Please join me in welcoming Paul.
Well, thank you so much. It's such an exciting event that we have going here, and we're going to have two panels in the next hour that are going to discuss aspects of the BRAIN Initiative. And the first panel is going to really be focused on the exciting opportunity and as well as the challenges that are there from the point of view of the science and technology. I think we all know that this is a field where there's just really very exciting, challenging, and no doubt extremely beautiful science that can happen. And one of the underlying questions that we'll be exploring here is what is special about this moment? Why should there be a BRAIN Initiative now? Have there been developments within neuroscience and within all the related disciplines, or even disciplines that can ultimately support neuroscience, that make this a very special moment? And we're very, very fortunate to have here two really wonderful panelists, Professor Corey Bargmann from the Rockefeller University and of the Howard Hughes Medical Institute, and Professor Mark Schnitzer from Stanford, and also of the Howard Hughes Medical Institute. So we're so fortunate to have you here. And so let's start our panel here with Professor Bargmann. Professor Bargmann, your work has mapped the neural circuits in the nematode worm and observations related to the behaviors of the worm. So in many ways, we could say that you have laid the groundwork for the BRAIN Initiative. And so we're going to look to you first to give us some insights on this field and where you see it going.
Okay, thank you, Paul. So the goal of the BRAIN Initiative is to map the circuits of the brain, to measure the fluctuating patterns of electrical and chemical activity in those circuits, and to understand how their interplay creates our unique cognitive and behavioral abilities. And this is a special time to be working on this because we can really build on the neuroscience that's accumulated over the past 50 years that really accumulated in two different areas, one of which was the level of molecules and individual neurons, so the level of sort of a very high resolution, magnified understanding of neural processes. And the other was from neurology and from brain imaging, sort of understanding of large areas of the human brain and how those work. But there's been a missing level in the middle, and that missing level in the middle is really where we think that cognitive processes and processes like perception and memory and action are developing. And that's not at single neurons and not at sort of large blobs, but at networks of, in a human brain, millions of neurons that are acting together locally and over great distances, whose dynamics are constantly changing, and the flow of information of neuron from what to the next, and the transformation of this information by context or by emotional state or by experience gives rise to the incredible diversity of properties that a brain has. Now, what makes this the moment is that there have been advances in 3 areas that are making it possible to start to look at the brain at that level of the intermediate level of circuits and networks. And Paul asked me to talk also about the gaps in our understanding. And I would say that each of those 3 areas gives promise, but also points out what still needs to be accomplished and what the people in this room will have, I think, a great deal to do in terms of accomplishing. So the first is that now, instead of looking at the activity of individual neurons one at a time, neuroscientists can routinely look at hundreds of neurons, and some people can look at thousands of neurons at a time. And that is already showing us things about patterns of activity in the brain that we really did not anticipate from looking at neurons in isolation. And that's been an advance driven by new advances in molecular tools and new kinds of materials for recording. But we don't need hundreds of neurons. We really need thousands to millions. And there need to be incredible advances in optics to gather that information at speed. There need to be advances. The tools we have need to be 100 times better than they are now. The second is that once you see these patterns of activity, if you start to look now at the sorts of things people see, there's a wonderful movie of the brain of a zebrafish. And all these neurons are flashing on and off, and the first thing you realize is that you have no idea what it means. And that really, that one-minute movie poses the questions that you have to solve in parallel with just looking at patterns of activity. And that is, you have to know what the cells are, and you have to know how they're connected to each other. And so moving downward to that level of understanding where the activity comes from is really critical. And again, this is something that's been done in the past, but is now going to have to be done on a scale that is so much larger than it's ever been done for. And when we think about these kinds of reconstructions, the kinds of data analysis and image recognition work that's happening now in the technology world can be brought to bear on these problems in new ways that will advance them. And finally, information flow through these systems, just observing is not understanding. And in order to understand that, we have to be able to intervene, to perturb the flow of information, to see which parts of that activity are really critical for particular behavioral or cognitive states. And we need to ask also how small perturbations cause the whole pattern of neural activity to shift. And this is, again, an area where there's been just a lot of advance in recent years in the development of a method called optogenetics, for example, that allows manipulation of neural activity. But this needs to be so much more precise and so much faster than it is now to really start to interface with neural circuits in real time. And then meaning also comes from conceptual approaches, from modeling, from theory and computation. And those, again, are areas where we need people from the quantitative sciences, from statistics, from physics, from technology to think with us about how to develop an understanding beyond a description of the brain. And I think very close relationships between experimentalists and theorists are going to become more and more important as this moves on. So these are, in each case, there are opportunities, in each case, there are gaps. And I think this group of people stands to do a great deal to bring those opportunities and those gaps to the next stage.
Okay, thank you very much. We'll turn now to Professor Snitcher, who has really, if you haven't seen his work previously, has built miniature optical systems that allow his colleagues and himself that can be mounted essentially on an animal to peer inside their brains of mammals as they go about their business. And indeed, those miniature optical systems have exploited the remarkable discoveries of your colleague at Stanford, Carl Dieseroth, in optogenetics, which Professor Bargman was just referring to even modify these behaviors with light. And so these are really incredible examples of how light is being used to interrogate. And so we'd like to hear from you a little bit about this question of what is special about this moment.
Yeah, thank you, Paul. First of all, I'd like to thank all the leaders who made possible not only this event, but also the BRAIN Initiative. I think Corey laid out some of the key opportunities and challenges that we face in this initiative. And speaking as an engineer, I think it's a very exciting moment to bring together many of the elements that she mentioned, the exciting developments that have come to fruition recently in different sectors of the engineering world and of the technological communities. One of the most exciting things that's happened already in the BRAIN Initiative has been the energy and enthusiasm it has evoked within the engineering, information technology, and physical science communities in academic institutions and in industrial communities. And we've seen this in students and in senior researchers who probably never thought of themselves as being involved in neuroscience until recently, but are now beginning to ask how can they help and how can they get involved. And so, as Corey described, I think there are many important roles for engineering and new technology that will likely emerge in the BRAIN Initiative, and I expect the results will be profound by helping to unlock some of the central mysteries of brain function, by providing new tools and helping to lay the basis for conceptual foundations in our efforts to prevent and cure brain disease and brain disorders, and also in harnessing some of the brain's computational strategies for humanity's own technological purposes. And part of the reason that this is a very opportune moment for the BRAIN Initiative is that there already exist many different dazzling technologies that our engineers and technological industries have already developed. And I think that an important part of the BRAIN Initiative will be harnessing these impressive technologies from different disciplines and sectors and putting them to use, to new purpose in brain research. And so just to suggest a few examples of technologies that have emerged recently that I think may have very promising future for brain research. Just to suggest a few, in telecommunications, we already have very powerful wireless technologies, and these are poised to yield new methods of wireless brain recording. Image sensors and miniaturized optics in cell phone cameras are prompting new forms of tiny microscopes for inspecting brain activity. In semiconductor microfabrication, there are very exciting opportunities to create customized photonic detectors and sensors that may enable novel brain imaging systems. And likewise, the technologies that exist for inspecting semiconductor wafers in that arena may yield larger microscopes than available today in the neuroscience world for inspecting brain activity at a cellular scale and at the level of the many hundreds of thousands to millions of neurons that Corey talked about. The photonics industry also brings very powerful technologies to bear on questions of pertinence to neuroscience, including lasers, custom fiber optics, cameras, all of which may, when harnessed appropriately, may allow us to visualize facets of brain activity that we have never imagined even existed before. In military defense, there are digital imaging technologies and surveillance algorithms that may help us track and analyze the movements and behaviors of small model organisms that are widely used in brain research. Adaptive optics, computational optic methods of seeing through turbid media may help us create imaging tools, allowing us to look deeper into the brains of living animals than we've ever done before. Robotics offers methods of mechanization and automation for handling model species that we use. And of course, in computation and information technology, there are statistical learning methods that today might be used to track patterns of consumer behavior, but these same machine learning algorithms might yield new means of identifying large-scale patterns of brain activity and helping us understand how these patterns might go awry in brain disease and brain disorders. So part of the opportunity here is to capture and combine all these constituent technologies where possible. But to achieve these gains, and others that we have not even realized, it will be important for the technological communities, the engineering communities, to work very closely with the neuroscience community in a way that has scarcely happened in the past. But I think we really need to do this. The challenges are so great and important that we must collectively rise to this challenge. And I hope that a main facet of the BRAIN Initiative will see new levels of cooperation between different scientific disciplines and different fields to a degree that neuroscience research at least has never experienced before, but that has characterized previous presidential science initiatives. And if we can achieve this very tight level of cooperation between the neuroscience community, other science communities, and the engineering communities, then I think this will be very important towards making the BRAIN Initiative a wonderful success.
Great, thank you very much. So what I've heard from these two comments so far is that On the one hand, we have a tremendous, we have a gap. There's still a lot to be done at the molecular level and at the level of the science of individual neurons. And there's still a lot to be done at the level of very large-scale imaging, but nonetheless, there's this gap in between where the precise imaging in the sort of neural circuit, million neuron kind of range is really, that's where there's a very special new gap that's opened up. And at the same time, other disciplines have made these tremendous advances that could be harnessed for that purpose in terms of our ability to have new materials and new concepts in electronics and optics, new kinds of highly parallel data stream handling, advanced computation, all those things. So there appears to be this kind of wonderful convergence that's going to really create an opportunity for us. And I think one of the issues we're going to be struggling a little bit with, and we're going to talk about it a little both in this panel and the next one, is how are we going to get from here to there? Because we have these very diverse activities that have to come together. And so my first question to you is, and meanwhile, I think if you're writing questions down, they can potentially be filtered up to me here, because otherwise I'm just going to be asking the questions, which would be no good. So we have these two things, and we need to bring them together, and it's going to be, a complicated thing to do. And so for each of you, you must have considered this quite a bit in the past couple of years as this initiative has started to gain traction. What do you think are some new models or mechanisms for collaboration that need to be developed around the BRAIN initiative in order for it to be successful? Do you have some thoughts about that aspect of it?
So I'll start. This morning I was at an announcement of the first grants that the National Institutes of Health is funding through the BRAIN initiative. And one of the things that's really notable about those grants, and that's quite different from what NIH usually does, is that most of them represented collaborations between scientists who were neuroscientists and scientists from some other area. So there would be a chemist, a physicist, a material scientist, a nanoscientist as part of a collaborative team. And I think even expressing the importance of technology as an important step in itself has been something that hasn't necessarily been a scientific emphasis. And once that idea was expressed, it turned out that there was a hunger and good ideas for how to develop that. And I think, the ideas that emerged, in my opinion, were more interesting than what we had been thinking might have happened when we put together some of the ideas for the future, which is as it should be when many people come up with, you filter out the very best ideas for many people. The second thing is I think that this meeting is really important. I think one of the things that has not been easy to do until now has been to get together the leaders of different kinds of organizations. That my extremely limited experience of the government has been that the NIH is very good at interacting with the NIH, but that it's harder to bring in people from outside the government, it's harder to bring in the foundations, and yet many of the newest ideas are emerging in areas outside of the sort of conventional organizations. And I think having something where the BRAIN initiative has an identity, where people can know where to turn, where they can know where meetings are, where they can start to meet people from very different places, where the Intels and the Facebooks are represented in the room and not just the academics, is going to be really important for that next stage of development.
Mark, do you have some?
Yeah, I would build on that. I mean, this morning I was at a panel for the National Photonics Initiative, which brought together companies that until this year might not have thought of themselves as having offerings for neuroscience research. And I think that's going to be really emblematic as we try to bridge the culture divide between the neuroscience research community and other communities. I think that neuroscientists will be we're very pleased to find out that people have tried to address many of the challenges we face, but in other contexts. And learning what those other technologies are and seeing what might be available to try to solve some of the issues we face in neuroscience will be very rewarding. At the same time, physical scientists, computational scientists, and members of the engineering community may already have some very exciting solutions and technologies that they might not have considered offer utility for neuroscience research. And so being able to bridge these two communities and explore what they might offer each other and get them working together in a cooperative fashion, I think points to some very exciting times ahead.
Okay, very good. Yeah, I think that's it's very interesting. When you've mentioned that the new NIH funded activities have brought people together across those disciplines into working groups, and there's a certain level at which that's happening, and I think that's very exciting. And once you start to find that people are doing that, then they gain competitive edge a little bit by making that cooperation. And once it's clear that that road is a good one, then people will follow it, and it becomes a very exciting kind of a movement. I guess one of the things I'm thinking about a little bit is that there may be a need for this to happen at many different scales, all the way from perhaps even individual researchers who might ultimately be trained in the neurotechnology area, all the way to small groups, but then possibly even if we really want to integrate all these things together, we may need some larger groupings of people to come together ultimately in order to make all these pieces come together that are so diverse. So to me, I can kind of see an issue of needing to think about this at different scales of activity. I don't know if you have any opinions about that, but that's the thought. I'm eagerly awaiting your questions, and while we're waiting for those, I will put out there something which, Corey, you just alluded to, and this is an important question for discussion, not just in this panel, but I think, in all the other events that we're going to be having here around this. We have folks here from all these different sectors. There are, of course, real medical experts. There are frontline researchers from the universities and national labs whose expertise spans a very wide range of disciplines. There's some private foundations that are really breaking ground in basic and applied research in this area. There are a lot of industry leaders here who can help create a new economic sector, essentially. There are patient advocacy groups. There's a huge range of government agencies here that are all participating in this. And when I look at that, I have to say, I see emerging something that's very different than other science initiatives that we've seen previously. It looks a little bit different. And we're, I think, searching around for a model of what the Brain Initiative could turn out to be a model, really, for what a new type of science initiative is that integrates beyond the government activities and brings all these pieces together in a certain way. So maybe you have some thoughts on how we could do that, because it's going to be more than just a conference like this, probably, to make it happen, right? Any thoughts on that? I don't want to put you on the spot, but I think we need to be thinking about that.
Well, I think you're right in saying that this is happening at different scales. Even within individual universities, we're seeing students from diverse fields becoming interested in neuroscience because of the Brain Initiative, joining research groups they might not have otherwise. At the same time, at a broader scale, we're seeing organizations, research umbrella groups, thinking about reaching out to different communities, forming cooperative agreements, consortia, and so forth. So I think this kind of collaborative, cooperative spirit that we will absolutely need for the Brain Initiative is indeed, as you point out, happening at the level of individuals, but also happening at the level of organizations.
Okay, I've received some interesting questions, thank you. And I'm going to start with one that I'm partial to, so I get to choose, right? I mean, that's how this thing kind of works. That's why some people don't always like this method, because it's, the moderator can kind of bias things. But what can we do institutionally to foster the development of theories that bridge the gap between neurons and behavior? And I think this is a very core question. It comes from Gary Marcus from NYU. Thank you for asking this important question. And I think that it's really at the core of the initiative at some level. I mean, how are we going to actually improve understanding and not just provide lots of observations?
If I can comment, I think that theory has been very important in biology at a point that there was sufficient data, that there was a real conversation between the theorist and the experimentalists about not just how something might work in principle, but how something worked in real life. What predictions did this kind of a model or a theory make? How did that manifest itself in the next round of experiments? Were those predictions met? Does it have to be modified? And there is a real hunger for theory in neuroscience. And when you see the occasional theories that we do have, like the dopamine reward prediction error theory, which has ways of thinking about everything from the most basic learning of motor skills to models of drug addiction in humans, you see how powerful those notions are when we can develop them. And I would say that the trick is going to be really putting those people together. You know, the ideal would be that every brain initiative neuroscientist might have a theoretical partner or in some of these, and that conversely, every theorist would be really grappling with what experimental data really looks like instead of what you wish it looked like.
Yeah, you know, exactly. That's great. You know, there is a very famous, I guess it's a joke, from Ernest Rutherford, discoverer of the nucleus. And at one point, he said there are only two fields of science, physics and stamp collecting. And I believe he meant to be pejorative about the stamp collecting. But in fact, I do think that at some very fundamental level, there is a period required of observation that helps provide the lay of the land, the map of what's happening, and then, you know, theories can emerge. But that's not entirely satisfying, and I think the question does bear on this point of, you know, we need to, as you were just saying, we need to actually build that into the initiative, that it's an expectation that people should be pushing to have theories tested and not just, you know, performing the observation in isolation. Mark, you look like you want to jump in on that.
Yeah, I think the neuroscience community is very receptive to this. In neuroscience, we have one of the most successful examples of a theoretical contribution, namely the theory of nerve conduction from Hodgkin Huxley, and this is something that every PhD student in neuroscience learns. And then more recently, in the 1980s, there was a substantial influx of ideas from theoretical physics as neural network theory was developed, and also from theoretical engineering. So I think the neuroscience community already recognizes the importance of theory. This was an important facet of the NIH brain report that we wrote. So I think that the ground has been laid for a very strong theoretical contribution. And as Corey points out, I think the close interactions between the theorists and the experimentalists will be key. Theory is going to have very important roles for prompting new questions that experimentalists might not have thought of on their own, but they can address with the state-of-the-art tools and technologies that are emerging. And as also was stressed, we can't just acquire large data sets. We have to have conceptual advance that goes along with that. And theorists will have an integral role in helping us understand and interpret the state-of-the-art data sets that we aim to acquire.
Very good, thank you. So now we have a pair of questions that are a little bit more focused in, but very important. The first one is DARPA has made breakthroughs in human-computer interaction, from remote control of cursors and computers to prosthetics. How will the Brain Initiative leverage that research? So perhaps either of you has a feeling for that question.
I'm actually looking at a person in the room who was involved in exactly that work, John Donahue. And I would, you know, I think that one of the advantages of the Brain Initiative as it's developed has been that different groups have started out with an emphasis on what they do well. That DARPA, for example, has already started funding initiatives, including initiatives based on deep brain stimulation, as Daria was telling you about, initiatives based on trying to do memory restoration, that really plays off of their particular strength and interest in the more device-oriented, engineering-oriented part of solving real-life brain problems. And but you know, many of those things have been built on a foundation of science that was done at a basic science level. So one of them does not replace each other. They really complement each other.
Indeed.
You know, I think one of the things that as a community we're appreciating more and more is that diseases that might have seemed disparate, in fact, have some common elements. And by building a platform of knowledge and a platform of technology, through the BRAIN Initiative, we can try to make advances across diverse areas, or areas that initially seemed diverse. And so by pushing forward our basic knowledge, but also our basic technological capabilities, there will be future opportunities for specific projects to develop very exciting technologies that will bring forth technologies that may even impact human health that we never would have thought possible without the groundwork that the BRAIN Initiative lays.
So this next question, I think, is very connected, because the previous one was human-computer interaction. How do we exploit it? This one is related, but I think it takes us to an interesting place, because it also deals with certain aspects of the interventions that are involved potentially in this. How do you think the BRAIN Initiative should work to advance understanding of the human brain non-invasively at the system level?
So that is an absolutely key transition that has to happen between animal and human neuroscience. And I would say that one of the areas of the new NIH grants actually that I found most appealing when looking at the new funding opportunities is the number of people who are thinking of completely new ways of interacting with human brains non-invasively, of using methods like PET and MRI in a mobile platform instead of shutting you inside a box, of trying to think of completely new ways of interacting with brain modulation through magnetic fields or through focused ultrasound. And I think that, again, this is an area where the physical sciences can combine with what is being learned in biology to advance things. Which of these things will work? Who knows? But if 20% of them work, if just a couple of them work, they could really change what we can do in terms of examining the human brain in natural conditions at speed.
I would make 2 points in this context. I think that there are possibilities for new physical imaging and perturbation modalities that have only just begun to be considered. There's a history in physics and technology of effects that once seemed esoteric, eventually finding their way into standard fare. And so new modalities that might be based on effects such as magneto-optics and other fairly nuanced physical effects offer some interesting promise. And as Corey said, only a subset of these will eventually pan out. But obviously, creative thinking regarding new physical effects, new ways of interrogating the human brain non-invasively will be very important. Secondly, this is a key area where I think that coordination between researchers looking at animal brains and researchers working in the clinic with human brains can really pay some dividends. So for example, there are certain signals that we can record non-invasively in the human brain. And in animals, we could record those same signals, but also look at the underlying cellular basis for these signals and get a deeper mechanistic understanding of what might be causing the signals that we can record non-invasively in the clinic. And that also will deepen our understanding of what we can measure in the clinic and hopefully point us towards new diagnostics and new therapeutics.
Okay, Professor Bargman and Professor Schnitzer, I want to thank you very much for helping this panel to start the discussion about the science and technology side, and we're now we're going to switch over to your colleagues. So while our two new panelists are coming up, I'll start just by saying that the BRAIN Initiative, of course, really it's exciting science, and it's going to be also, I think, really wonderful, beautiful science. But the work itself is really it's really ultimately geared towards helping people in society, and we really are going to need to organize ourselves carefully to make sure that, that we do end up having the kinds of impacts that we're looking for, that we all hope for. We know that there are instances really of traumatic brain injury and post-traumatic stress disorder, to just name two, that are really, really devastating in our society and that are really affecting huge numbers of people and their families. And so in this panel, we're really going to be exploring these aspects of the impacts on our society. And we're very, very fortunate to have a wonderful panel here. We have Jeff Manley, who's Chief of Neurosurgery at San Francisco General Hospital and Professor of Neurosurgery at the University of California, San Francisco, and Carrie Ressler, who's Professor of Psychiatry and Behavioral Sciences at the Yerkes Research Center at Emory University, and co-director of the Grady Trauma Project. Now, Professor Manley, you're a trauma neurosurgeon. You have clinical interests in brain injury, spinal cord injury, critical care. Your work is on the front line of clinical research at SF General and at UCSF. And you have remarkably wide-ranging interests when I looked up what you were working on, even though we're neighbors living both in the East Bay and all that, you know, gaps exist. But your work reflects an astonishing range of research interests, all the way from really molecular aspects of brain injury to the clinical care of head trauma patients. So please give us your initial thoughts on this.
Sure. Well, I'm honored to have been invited today to speak on behalf of my co-investigators and really the TBI community at large. Traumatic brain injury and concussion are really no longer the silent epidemic that we referred to 10 years ago. Traumatic brain injury is now known as the signature injury of the wars in Iraq and Afghanistan. There's growing awareness of concussions in a variety of sports. And we now know that it's really more than just an event. It's really a process that in some individuals can lead to lifelong disability. However, military and sports TBI are really only the tip of the iceberg with traumatic brain injury. Traumatic brain injury happens all around us. There's at least 2.5 million people in the community every year that sustain a traumatic brain injury and go to a hospital to seek help for this. And there's probably at least another 2 to 3 million folks that are never even seen by the medical community. So we really do have an epidemic of traumatic brain injury, and this has been with us forever. It's just now we're becoming progressively aware of this. We have millions of people that are permanently disabled from traumatic brain injury. The cost estimates are in excess of $70 billion a year. Unfortunately, what we know about traumatic brain injury is probably 40 to 50 years behind what we know about things such as cancer and cardiovascular disease. TBI is one of the most complex injuries and the most complex organ in the body. We just heard about all these very complicated integrated circuits and so on, and then we lay upon this a very, very complex injury. And it's no wonder that this is a very, very challenging problem. And this problem is so complex that not one investigator, one institution, or one company, or one agency is going to solve this problem. We really need everybody coming together to work together, which I think is what's so exciting about this room, is we see all of the stakeholders sitting here today that could really come together to try to solve this problem. Our recent, and I liked your quote there, I used to be a theorist and now I'm a stamp collector, but I have really cool tools these days.
Stamps are beautiful.
So our recent efforts with Track TBI and the new TED initiative, I think demonstrate the potential of these robust private-public partnerships to be able to address this in a multidisciplinary fashion. When I look back over the last year in our work with companies such as General Electric and philanthropic organizations such as One Mind, I see people coming together across multiple disciplines, really with funding from both the NIH and from the DoD to be able to address this problem. And I think we're starting to make a little bit of progress. So as we've just heard from Corey and others, there are lots of very, very exciting things going on in the Brain Initiative, how groups of neurons speak to one another, how they work in large, complex circuits, and how we can start to manipulate this, whether it's through devices or whether we can do this with optogenetics. However, I think that we have to look at our field and is the clinical realm ready for this? So you're right, I have a broad training background. I'm a product of the medical scientist training program, having done a basic PhD in neuroscience and going on and training as a neurosurgeon. And so, my role is to really try to stand in the middle of this. And when I stand in the middle and I look at what's happening from the basic science aspect and then I see what's happening in the clinical realm, we've got a lot of work to do in the clinical realm to really get ready for this. So for example, today in traumatic brain injury, we take this complicated injury and this complicated organ and we use a classification system that was developed 40 years ago. And we call traumatic brain injury mild, moderate, or severe. Okay? Can you imagine us trying to come up with a treatment for cancer, calling that mild, moderate, and severe? Not a chance, right? So there's the reason why we're not making a lot of progress. Concussion. We have 42 definitions of concussion. And that means that nobody knows. We've got to have more objective tools. We've got to have the kinds of things that are coming out of the Brain Initiative, whether it's an imaging technique or it's some sort of non-invasive brain function monitor, to be able to objectively get past all of these symptoms to really try to come up with an objective way of looking at that. So as we look forward, I really think one of the solutions, as was really advocated by the National Academy of Sciences a couple of years ago, is a precision medicine approach. What do I mean by a precision medicine approach? We need to embrace the complexity of TBI, and we need to understand that there's things happening at the genetic level. There's proteomic change. There's changes in the imaging. There's changes in the clinical features. And importantly, we can't just use a simple disability measure to look at traumatic brain injury. We have to look at things like memory and learning and borrow from the basic science community and translate that to where we're really comparing apples to apples as we try to move what's happening from the rodents and the other types of animal models into human biology. I really think that in order to do this and to build these multiscalar models, we've heard this before, it's going to really require a lot of technology. The idea of being able to integrate a gene with a voxel image with an outcome measure doesn't currently exist. And I am sure that there are companies that are in the room today that have the kind of technology that have been used in other areas that can be repurposed to help us to achieve this goal. I think the brain injuries and neuroscience in general really is the final frontier of medicine. We can make progress, but this is going to require a concerted effort. This isn't just a 1 or 2 year grant proposal. This isn't a 5-year grant proposal. We are going to need continued and sustained funding. This is a big problem, and nobody wants to hear this. We're not going to solve this next year. This is something that we've got to get behind and have a multi-year sustained commitment in order to be able to make a difference. I do believe that with vision, sustained commitment from multiple partners in a multidisciplinary fashion, and most importantly, a word that we've heard already, and I'll say it again, collaboration, 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 we can make a difference for our citizens, our soldiers, and our athletes with traumatic brain injury. Thank you.
Thank you. Now, I do want to ask that if you have questions, there were a lot of ideas there, signal please to the folks with the cards and start writing them down now so that we can be ready momentarily for starting to get them to come in. Professor Ressler, you have focused on the molecular and cellular mechanisms of fear learning and the process of extinction of fear in mouse models to improve our understanding of and advance treatments for fear-based disorders such as PTSD and traumatic brain injury. We'd love to hear from you.
Thanks so much, Paul. It's really an honor to be here. The World Health Organization has reported that mental illnesses are the leading causes of disability worldwide, at a cost of tens of billions in the US and trillions worldwide. Among both our military and our at-risk civilian populations, PTSD is among the most prevalent and debilitating of the anxiety and fear disorders. About 7 to 8% of the population will develop PTSD at some point, and that's much higher in the traumatized risk population. Over 5 million adults have PTSD during any given year. Yet this is only a small portion of those who've gone through significant trauma on the battlefield, as well as in our inner cities and other high-risk areas. Furthermore, women are twice as likely to develop PTSD, with about a 10% developing it at some point in their lifetime. The symptoms of PTSD most notably develop in the early aftermath of a trauma, the weeks to months following the trauma, but they can last for years to decades to a lifetime. They include overwhelming fear, intrusive memories, avoidance of trauma reminders, hyperarousal, among others, including one of the most common causes of depression. These symptoms can be overwhelming to the victims. They're often referred to as an emotional black hole that you can't escape from these memories. Those with severe PTSD often generalize these symptoms. They can have difficulty holding jobs, keeping relationships. They can become paranoid and have erratic behavior, all from this underlying extreme fear based on past memories. It's a severe problem in our veterans who have given their life for our country, and it is an under-recognized, near epidemic proportions in our inner cities where violence, drugs, and fear are the rule. At a time where there's so much promise in our nation and the world, it's shameful the disorder of fear prevents progress for so many. But science offers hope. PTSD offers an ideal opportunity to study environmental and biological factors that result in the development of pathological trauma responses. Because we know when it starts. It's the only psychiatric disorder we say we know when it starts. It starts at the time of the trauma. It may be amenable to interventions initiated shortly after the trauma to prevent its development. New rationally designed treatments that derive from basic neuroscience and preclinical animal and human studies are currently under investigation worldwide. Remarkably, the same brain regions, the amygdala, the hippocampus, the insula, to name a few, are involved in fear processing from mice all the way to humans. Therefore, PTSD and other fear disorders may be among the most tractable targets in psychiatry because we understand a lot of the circuitry already. We are now beginning to functionally dissect, using the kind of tools that have been talked about, optogenetics, engineered dreads, and others, to dissect specific cell pathways within subregions of the amygdala that can specifically turn on the fear reflex or turn off the fear reflex in a rational, designed way. They can regulate this fight or flight response. Further understanding of the molecular, cellular, and circuit mechanisms underlying fear will have huge implications for the millions of people suffering from PTSD and other fear and anxiety disorders. But we need your help. The Framingham Heart Study, started in the 1940s, marked a watershed event in utilizing large cross-sectional, collaborative, and prospective research to identify risk factors for cardiovascular disease, changing the prevalence, treatment, and prevention strategies for heart attacks, strokes, and related illnesses in the meantime. It is time that we do the same for mental health. As a beginning, several ongoing initiatives between the NIH and the military, including the Army STARS Project, Strong Star, and others, are beginning to provide some similar large scientific cohorts for mental disorders. But the field needs support from private partnerships as well, since this cannot be done by the government alone. For example, the Human Genome Project led to the more recent Psychiatric Genomics Consortium, which has led to huge success with very large collaborations of hundreds of thousands of samples, leading to new discoveries in schizophrenia and autism, which are leading to understanding at a molecular level of entirely new approaches to these very debilitating disorders. We need to do the same for other disorders of the brain. Up to 40% of PTSD, much of the difference between risk versus resilience after a trauma, is genetically determined. Consortia are underway to uncover the genomic architecture of PTSD through similar large-scale collaborative studies. By identifying its genetic pathways and integrating that knowledge with the neural circuits that we're starting to understand related to fear, we can make great progress. Every day, promising advances are being translated from basic science to the clinic, including methods to interfere with fear development after a trauma and prevent PTSD from forming initially, as well as techniques to augment therapy by normalizing the fearful emotional memories. Invasive treatments that affect disrupted emotional circuits, such as transcranial magnetic stimulation and deep brain stimulation, are borrowed from neurosurgical interventions and attempt to regulate the known brain targets discovered from neuroscience. Other approaches include drugs that are given at the time of specific learning events to enhance or disrupt emotional learning with talk therapy, derived from neuroscience of learning, memory, and brain plasticity. Neuroimaging shows us that common brain regions are targeted with both biological treatments and emotional learning. By understanding the roles of specific molecules and cells, circuits and pathways underlying fear and emotion, we'll be able to target both the prevention of PTSD at the early hours on the battlefield or in the emergency department, as well as to utilize new targeted and powerful approaches to treatment and recovery. But to do this, the field needs your help, and we need a greater understanding of the brain. Thanks.
Thank you very much. So I think I detect a common theme there, which is that in both areas, you have already taken steps of using some of the most recent advances in the molecular science and in science that's taking place at the level of neurons and so on, that you've been integrating that already into your programs, and I think that's very exciting. And I'm wondering how you think that's going to work going forward. We talked earlier a little bit with the previous group about the ways to bring people together, and that there might be ways to do that at different scales, small scales and larger scales, education of individuals and so on. And you mentioned the Human Genome Project, Gary, which I think is a fascinating case. I mean, there, obviously things happened at a large scale. Church is here from one of the people who helped to guide us to that initiative, and I know that our lab played an important role in it at one time. But what my impression is that that project, although people were very interested in the implications from the very beginning, it took a while for that to kind of, and so the question is, can we make it happen a little bit faster this time by integration early? So I wonder what your thoughts are on that. What kind of practical things can we do to make it happen more seamlessly?
Sure. I think this is going to require collaboration and team science. We need to understand that we're looking at a human that's been injured, and we had previously been we've been reductionists about this. We had people that were doing MR imaging, and we had people that were looking at the genetics. And what we've done with some of these recent public-private partnerships that we've put together is that we brought together folks from the entire spectrum, whether they were interested in the acute phenomena, whether they were imagers, whether they were outcome specialists, and we've all come together to focus on the patient as the goal in a multidisciplinary way. And more importantly, some of the work that we're doing with some of our corporate partners, I think is very, very important, because ultimately at the end of the day, we need to commercialize what we're doing to get this to the patient's bedside as quickly as possible. And so when I look at, say, for example, our collaboration with GE, the things that we're doing today, I think will get to Casper, Wyoming quicker than they will at the research centers that are doing this, because we're not waiting to get an answer. We're actually getting the answers together, and by getting these together, they're being able to be disseminated and distributed out into the public much quicker. We want to accelerate research. I take care of patients on the front line. I have families asking me every day, will my kid be able to graduate from high school? Will my husband ever go back to work? And I don't have those answers. So I was joking earlier, we are doing a Framingham-style study of traumatic brain injury. We're collecting the stamps, and we're trying to understand what this looks like. All I want right now is to move past mild, moderate, severe, or concussion. I want to be able to sit there and tell a family, here's the probability that you'll go back to work. I think it starts with diagnosis, and from diagnosis, then we'll get more targeted therapies. And as we're working with our folks and all the amazing things that are happening in the Brain Initiative, this will then filter into the work that we're doing, but it requires a lot of communication and collaboration. We don't need to wait, otherwise none of us will be here by the time we come up with treatments for something that people need right now, today.
Just two brief thoughts. One, I think, related to the points that were discussed earlier with how and what sort of non-invasive tools can we use. We really need biomarkers, whether they're blood-based biomarkers or whether they're neuroimaging biomarkers that will give us intermediate diagnostic measures beyond our clinical observations. And then we need to find ways to build on the enormous success of molecular genomics and human genetics, and how do we take the great engineering tools of neuroscience currently and bring genomics and genetics and epigenetics to that, to understand how every neuron is really its own factory working with this epigenetic system.
Thank you. So here's a question from the audience, and this one comes from Amy Nutt from the Washington Post. In reference to recent research out of Northwestern, how far away are we from being able to image brains of trauma victims immediately after the event to determine who is liable for PTSD?
Well, PTSD, I thought TBI was going to be the answer. I think
Well,
we're getting,
I'm sure both are.
we're getting closer with TBI.
But I mean, I think this show, people want to know.
Right. So there are techniques that Jeff can say a lot more than I can about, whether it's DTI or DKI and some other methods that are very sensitive to white matter, slight disruptions that we're looking at. And as Jeff and I were talking about beforehand, it's increasingly looked at with whether it's neuronal disruption or inflammation or other sorts of measures, that physical trauma and emotional trauma seem to do many similar things on the brain. So how quickly will we be able, with a brain image? I don't think at a structural imaging level we will be able to. It's possible that with functional imaging, whether it's resting state, which is very easy to do anywhere quickly, or with other approaches, as we understand more of the bioinformatics, which are extraordinarily complex, but simply the resting state, what the brain is doing alone while lying in a scanner, has an enormous amount of information that we've only begun to tap bioinformatically in the field. And that can tell us an awful lot. So I think there is hope.
I guess also we're obliged a little bit to come back to the question of Gary Marcus from earlier, that if we don't have a kind of theory for understanding how these behaviors arise, then it's going to be difficult to be very predictive about things, perhaps correlational and observational at first, but it will evolve in that respect. Here's a second question from the audience. What are examples of successes from recent advances in cellular neurobiology that have already translated to meaningful therapies? What could we learn from these to apply to future advances? And the question is from Victor Krauthammer from the FDA. You can understand why they would be wanting to
Certainly.
answer that question. Yeah.
Well, I wish we had a therapy. 2 Saturdays ago, we announced the failed trial for progesterone, which was based upon 17 years of work with 200 positive papers in a variety of preclinical models, and yet this didn't translate into the clinical arena. So I think that what we should recognize from that, and I'm looking forward to the opportunity working with the FDA with this new TBI Endpoints Development Initiative, which is really trying to take us, again, we're talking about how to work with companies. We also need to be working with the FDA to understand this, that the kind of tools that we've used to stratify patients for clinical trials and the way that we've looked at the outcome, we have to throw away. This was our 32nd or 33rd failed trial. This is just not going to work anymore, and we've got to do a better job. So what I would say to our FDA colleagues is that we need to look at, this is a very complicated problem. Back to the question of the Washington Post, everybody's looking for that one tool, but there's not one tool. If I had chest pain this afternoon and I then go to a local hospital here, is it because of what I ate for lunch, or is it because I'm stressed out because I'm in front of all these people? They're not going to just say, well, your chest pain is mild, moderate, or severe. They're going to run a bunch of different tests. So this idea that one imaging tool or that one biomarker or that one EEG is going to help us to sort of stratify these patients, it doesn't work with the heart, and the heart is admittedly a much more simple organ than the brain. I think this idea of sort of the one shot, so we've got to basically, I hate to say this, but we have to just stop. We have to blow the whole thing up and go back to square one and say, okay, what do we know? What do we don't know? We don't know a lot, but where are we going to start? And we need to look back to our basic science community and look at things like memory and learning tests and look at behavioral assays and really try to replicate and translate this to get us across what is this huge valley of death and things like traumatic brain injury and many of the mental health diseases that we try to study.
I'm hopeful that PTSD is more hopeful than TBI at this point. And I think that's because I think PTSD in writ large is many, many things. And one thing we're clearly understanding, and one thing I like to say to my students is, about half the genes in the genome are relatively specific to the brain. And yet we have in the mental health maybe about 8 clusters of disorders as opposed to literally hundreds to thousands of medical disorders. Clearly we're lumping things together that are discrete disorders in the genomic realm. That said, I think there's components of PTSD that really do offer low-hanging fruit. I think psychiatry and mental health disorders are going to be a very broad range of things. Some things are going to be like cancer, and it's going to take decades or centuries to get them all. But I think there may be some things that are solvable. And from Pavlov to Eric Kandel, we've studied as a civilization learning and memory for over 100 years, and a lot of progress has been made. And neuroplasticity, learning and memory has been some of the areas of the most progress in the last 20 years. And there are a number of study drugs that are now being looked at in humans and have had a number of small positive trials that were based in mouse and rat studies, specifically understanding of things like NMDA receptor regulation. There's new things based on BDNF regulation, other sorts of channels involved in the learning and memory plasticity process, and a lot of epigenetic regulators that are also being looked at that really do offer hope. And they may not solve the broad PTSD that is chronic and has become depression and has become substance abuse and multiple things, but we do think that an animal model of fear learning is a good model of human fear learning, and there are certain components of this that are quite tractable, I think.
Very interesting. Okay. I'm going to take just a flyer for a moment here and describe something that I think relates to this indirectly, so bear with me momentarily. But last Friday, I was with a group of other scientists from around California. We visited the folks at IBM. Demendra Mota is sitting here. And at that group, there was some astonishing work in the Synapse project where they built circuits that are neuromorphic. They don't really look like brains exactly, but they're inspired by brains. And for those of you who haven't had a chance to see that work, it was published recently in Science Magazine, that group has taken this neuromorphic computing and machine learning idea, and they've been able to perform some image recognition computations with better than consuming power that's only maybe 1/1000th or less than what would be consumed if we had a conventional computer doing it, and also with some very high speed and accuracy. And so it's fascinating. But what was one thing that just made me think of what you're talking about is, of course, their circuits will sometimes have broken pieces, and pieces will kind of break in the middle. And they have these algorithms that will kind of learn to take advantage of the parallelism and go around and essentially create plasticity in an artificial system. And it seems like from those kinds of experiences, maybe we could learn things about, we know that the brain can do similar kinds of things, and we'd like to understand how that really works. And so it just feels like that's an area where, we really need to have some new discovery, and perhaps you have some thoughts on that.
Yeah, well, and again, I think we heard Corey talking about perturbation of a system. Well, when you injure your brain, you perturb the system. And imagine the power of looking at the connectome of an injured brain versus the connectome project that's going on now. Very, very powerful. I think that there actually are a lot of opportunities when brain-injured patients come to us and they can't speak, and yet a year later they speak. That's plasticity and repair happening right in front of you. And so with some of these emerging techniques with, for example, resting state fMRI and some of these structure function ways of looking at the brain, I think we're going to get a tremendous insight. I don't mean to come off by saying that we're really lost here. I think the first step to getting someplace is to realize that you've got an issue, to address it and to move forward. I think that there's many, many things. I mean, just some of the MR work that we're seeing that's identifying patients that currently we use CT scans when you come into an emergency department. I think within the next couple of years, the work that we're doing now will have you looking at MRIs. That's going to be an immediate advance and help for people that have traumatic brain injury. So I think there's a lot of opportunities, but again, as I said earlier, we really have to do this working together as a collaborative group, and I'm very, very encouraged with the spirit of collaboration that I've seen here and with some of these emerging multidisciplinary sort of big team science efforts.
And I just hit on that too, because I think it's a beautiful way of saying it, that most of our treatments that we currently empirically found probably aren't getting at the underlying pathology. Right. And in the same way, whether it's deep brain stimulation or whether it's enhancing plasticity, there are lots of ways, you can fix something without understanding the pathology, just like we had pacemakers that were very useful long before we understood mechanisms of arrhythmia, and I think there's something to be learned from there.
Thank you very much. Well, I think I can say on behalf of all the folks here how thankful we are to have you working on these critical issues that affect so many people, the traumatic brain injury and the post-traumatic stress disorder. And those are two very critical examples, but as we all know, there are many examples where, the illnesses associated with brain are so debilitating for people in society, and we all are going to try and work harder together to make some progress on this. So thank you very much.
Thanks once again to all of our panelists. I think they have given us a lot to think about. Our next speaker is Tom Khalil. Tom Khalil is the Deputy Director for Technology and Innovation for the White House Office of Science and Technology Policy and Senior Advisor for Science, Technology, and Innovation for the National Economic Council. In this role, Tom serves as a senior White House staffer charged with coordinating the government's technology and innovation agenda. He's been deeply involved with the BRAIN initiative since its inception and is going to share with us some details of the private sector commitments that have been announced today. Please welcome Tom Khalil.
Thank you. Good afternoon. And at the risk of sounding like I'm at the Oscars, I have a lot of people that I would like to thank. I want to start off by acknowledging a number of the people who worked really hard to make this event possible, and particularly Robbie Barbero, Robbie and his wife had a baby boy at 3 a.m. on Sunday, and he's working all the way up to that point to make this possible. Really cute kid. But I also want to thank Noemi Levy with the Domestic Policy Council, and Meredith, who's been doing a spectacular job as MC, Phil Larson, Kristen Lee, Faye Jenks, Randy Paris with the Office of Science and Technology Policy, and also Phil Rubin, who's been leading the broader White House Neuroscience Initiative. So please join me in giving them a hand. Well, as you know, when President Obama launched the BRAIN Initiative in April of last year, as one of his administration grand challenges, he issued a call to action to encourage companies, foundations, private research institutions, universities, patient advocacy organizations to join with him in supporting the goals of this effort. And this is really important because, as a number of the previous speakers have noted, we're going to be much more likely to achieve the ambitious goals of this initiative if we have a broad coalition of individuals and organizations, both inside and outside the federal government, that are providing their ideas, their financial support, and their expertise. And the administration has really been delighted with the thoughtful response to this call to action that we're announcing today. We've had a number of commitments from companies that have the potential to bring new tools and technologies to neuroscience of the types that the previous speakers were talking about. So members of the National Photonics Initiative, including Acumetra, Agilent, Applied Scientific Instrumentation, Coherent, Hamamatsu, Inscopix, Spectrophysics, and Thorlab will be investing at least $30 million in existing and new R&D to help achieve the goals of the BRAIN Initiative, and bringing the expertise in technologies such as imaging optics, laser sources, automated scanning technologies, and high-resolution cameras. GE today is launching a new brain health initiative that's going to build on and help coordinate their activities across not only their corporate venture capital, but their important work on open innovation, corporate R&D, and their healthcare lines of business. Google engineers are already building tools and infrastructure necessary to analyze petabyte scale data sets. That's quadrillions of bytes of information. I'm sure next time we get together we'll be talking about exabytes. But these are data sets that are going to be generated by the BRAIN Initiative, and they're already working with the Allen Institute, HHMI, and several academic partners. GlaxoSmithKline is providing up to $5 million in new funding for the research community to develop innovative peripheral neurotechnologies which could help develop treatments for chronic diseases such as asthma, hypertension, and arthritis. Inscopix is doubling the number of grants that they're going to award to researchers to help them image and interpret large-scale neural activity. Carl Zeiss Microscopy and UC Berkeley are teaming up to invest $12 million in the development of neurotechnologies, including the Berkeley Brain Microscopy Innovation Center. And there are a number of other universities that are making investments that are aligned with the BRAIN Initiative as well. So the University of Pittsburgh is announcing $65 million in funding for the University of Pittsburgh Brain Institute. Carnegie Mellon University will be providing $40 million over the next 5 years for its Brain Hub initiative, with support for new faculty positions, graduate and postdoctoral fellowships, and seed funding for research. The entire University of Texas system is rallying behind this. They've organized a multi-campus neuroscience council in response to the BRAIN Initiative and have already committed $20 million for equipment, faculty recruitment, and access to its cutting-edge supercomputer. The University of Utah is committing $10 million to launch an interdisciplinary neuroscience initiative. Boston University is launching multiple research centers in areas such as neuroimaging, systems neuroscience, and neural technologies. And several foundations are making investments that are also going to advance the goals of the BRAIN Initiative. Earlier this year, the Simons Foundation announced a $62 million Simons collaboration on the global brain which seeks to uncover patterns of neural activity that produce cognition. The Children's Neurobiological Solutions Foundation is expanding their pediatric brain mapping project with a goal of doubling the number of children that are participating in the project from 5,000 to 10,000. The Brain and Behavior Research Foundation is increasing its support for the most promising young scientists involved in neurobiological research. And we also have a number of organizations that are interested in fostering the technological innovation that is needed to achieve the goals of the BRAIN Initiative. It's the basic and fundamental research is great, but if we want to actually see these new tools, we're going to have to see the emergence of regional clusters. The Pacific Northwest Neuroscience Neighborhood will work to promote a vibrant neurotechnology cluster in Oregon and Washington State. The Neurotechnology Architecting Network is committing to mentor and train innovators who will design, prototype, assess, and distribute at least a dozen technologies for mapping and recording neural circuits. This network aims to create a distributed neurotechnology valley that will disseminate these tools both to advance fundamental understanding and to advance clinical applications. And in addition to all these new commitments, I want to acknowledge that 3 organizations that supported the BRAIN Initiative from the very beginning have made remarkable progress since the President's announcement in April of 2013. Consistent with its 2013 commitment to invest $60 million a year in projects and partnerships related to the BRAIN Initiative, in 2014, the Allen Institute completed the Allen Mouse Brain Connectivity Atlas and helped establish an annual conference for large-scale brain initiatives with the Keystone Symposia. The Howard Hughes Medical Institute invested more than $70 million to support the goals of the BRAIN Initiative during the last year, with a focus on developing new imaging technologies and understanding how information is stored and processed in neural networks. The Kavli Foundation, which played a very important role in the early discussions about the BRAIN Initiative, plans to endow 2 new neurosciences institutes by the end of 2015. Working with GE, HHMI, and the Allen Institute, the Kavli Foundation has also been supporting Neurodata Without Borders, which is getting the research community together to work on important things like metadata standards. So this is really, in a short period of time, an exciting set of commitments. So please join me in congratulating the individuals and organizations that made them happen. Finally, I want to note that I hope that this is just the beginning and that the BRAIN Initiative will continue to serve as a catalyst for investments by companies, foundations, and philanthropists, private research institutions, universities, patient groups, professional societies, and regions. And Paul, I think, gave us a really important challenge, which is it's great to occasionally pull all of you together and to see this really exciting, multidisciplinary, multi-sector group of people. But one important question that Paul has given us is how do we sustain these things, and what is the right level of organization from the small team to some of the complex systems engineering projects that Mark was talking about. So food for thought, and we're now going to have a great panel where you'll learn the remarkable progress that the science agencies that have been leading the BRAIN Initiative have been able to pull off since the President unveiled this in April 2013. So again, thanks for coming, and thanks for the remarkable progress that you have all made in such a short period of time.